I have some copy of the silver on the, I'll put that down. You got a hard copy?
I don't know.
Don't worry about it. Trying to figure out when it is. That's the year. Probably want to do it before homecoming, if I know, to keep them long enough to know. Homecoming kids, everybody just disappears. Out of nowhere. Yeah, I taught this class for so long, man. I'm just telling you, I had one student, he disappeared like 2 weeks before homecoming. And he came back 2 weeks after homecoming. Like, what can I do to catch up? Pre-register. Like, no, we're not doing it. I'm not breaking my neck now, busting my behind every day. And you take 4 whole weeks off and it just pop up. And all our time is valuable. You know what I'm saying? Mine and yours. So choose wisely. All right. All right. So we're going to do a few more examples today with these arrow pushing mechanisms. And we're going to actually start radicals today. If you watch that little Pac-Man video, I know it's corny and goofy, but the point was to introduce you to radical substitution. You laughing? You said it was corny. That was the intent. But that was the intent, though, to be goofy, right? But it was to make, hopefully make it make sense. So when we do it today, it won't be so esoteric. All right. I want to do the bottom 2 reactions because that's really one big reaction. And I also want to do the top reaction. I'm going to leave the 2 middle reactions for those who are on Zoom, those who are present. We want you to do those on your own. All right. So those you can do on your own, those 2 in the middle. That's really also one big reaction, right? You can see it's a proton transfer and then loss of leaving group. So it's kind of like a precursor for either for substitution. Let's do the top reaction. That's a reaction that, well, I'm not sure if they're still doing that in organic 2 lab, but that used to be our staple reaction, the aldol reaction. So here, what happened? So let's answer that. Let's answer the questions. What type of reaction is it? Then let's go through the thermodynamic component and ask about delta H, activation energy, KEQ, delta G. All right. So what happened in this particular reaction?
The python was broken on the second portal.
Right here?
Yes.
I agree with that.
And then
What caused it to break? You're absolutely right.
was it a sigma bond being created between the CH2?
Yes. So this carbon right here and this carbon right here. Is that right?
Yes.
You can see those 2 carbons are bonded in the product. Right? If I put the arrows in, this is my nucleophile. This is my electrophile. Within the electrophile, let me fix that. All right, there's a big dipole right here, so that's telling you where the reaction is going to take place. Always look for that. Anytime you want to figure out in an electrophile where the reaction is going to happen, always look for the most polarized bond. Once you find that and figure out which end of that bond is partially positive, that's the answer. That's why we spent so much time at the beginning learning about dipoles, learning about polarity, learning about electronegativity differences and all that stuff. We did it on purpose. That's the foundation for all this is predicated on that. All right. So now we can just put the arrows in. Anybody else? Or is it just me? You're not? Right. So what would the arrow look like in this case? Nucleophile attacking electrophile.
Since that, my bond is being, broken because the chunk there is moving from 5 bonds to that,
Oxygen.
to the oxygen.
Uh-huh.
Then you only have 3 bonds, three bonds to that carbon.
Okay.
So then you can move the electron
Here.
from the C over there, because you only have 3. So going out there, we can 4.
Like that. Good. Now, I like how you explain that. The fact that the power ball moved here, but it's actually concerted. So as these electrons are coming in, these are moving up. So it's all happening at the same time. Yep. But the polarity part, you're right. If I would have just asked you to draw a resonance for it, then you would just shift the power bond up to oxygen and that carbon will be positive. That's exactly right. All right, questions online. You got to unmute to ask because I can't see the chat. So any questions? All right, so that's how we got to here. But keep in mind, your nucleophile is your source, your electrophile is your sink. And electrons always move from source to sink, never the other way around. Always source to sink, always from electron rich to electron poor. All right, now let's go through and do the thermodynamic part. So what is delta H? What is activation energy? What is KQ? What is delta G naught, which is the Gibbs freedom? The hardest part is calculating delta H. That's going to give us the data to extrapolate all the other values from. So how do we calculate that? What are we looking for? So once broken, that's the formula that we can plug numbers into on the Bond's form. Is that right? Mike, I saw you with the chart up. What did we break? Carbon, oxygen, power bond. How much does it cost to break that? $741. And then what do we make? Carbon sigma. We made this bond right here. How much does it cost to, or how much energy is given off when you make a carbon sigma bond? So I got the chart here, but it's way up at the top. 347 kilojoules mole. We can already see that this is going to be a endo or exothermic process. Endothermic, because the delta H is going to be a positive number. What is that? 404? No,
that's like 390.
394. Yeah, 394. My bad. Positive 394. That's a lot. This type of reaction, a lot of times, is going to require a catalyst. That high delta H, high positive number like that, this is not a spontaneous reaction. it's gonna require catalysts in order to make it go. But I don't wanna get into that, but this is probably one of the premier ways in organic chemistry to make what they call beta hydroxy ketones. You can see right here. I take that alcohol that's protonated, that's going to take the oxygen and pronate it to the alcohol. And that's a very, very important functional group motif in organic synthesis. All right, so plus 394. What does that mean for the activation energy? Very high, right? Because the reaction is endothermic. What does it mean for KEQ?
It's less.
That's the one, good. And delta G naught, what is that? Is that also positive or negative?
Positive.
It's positive. And the reaction overall is endothermic. Endothermic. Any questions about that one? All right. Let's go to the bottom set of reactions. This is the overall product right here. It's actually, I have it written in 2 steps, but it actually happens all at once. That's the bottom. The bottom product is overall, like what comes out of this process. What type of reaction do you think this is? The bottom, so these two are connected. But the overall product is here. It's an elimination. Good. We didn't do up top. This is an addition, right? Added something to a pie bar and it's broken. Here, this is an elimination overall. All right, so let's do the top half, then we'll do the bottom half, and then we're going to sum up the delta H values to see what we get, whether it's overall exothermic or overall endothermic. Right? What happened up top? Going from here, what's that, to here. What happened? What's missing?
You removed the hydrogen.
I removed the proton.
Yeah.
Good. How did I remove it?
By taking that electron out, the extra electron attached to the oxygen, and attached it to where that hydrogen was forming the carbon,
Good.
and then you move the hydrogen over
Okay.
to combine to the oxygen.
Okay, good, good. So I use this to do proton transfer. That's what this process, this first part is. Proton transfer. Right? So the mechanism for that is just like we just studied with acid-base chemistry. Is that right? If the OCH3 is a base, this proton is acidic. And so let's look at what happens. All right, so I'm gonna put an arrow in here, boom, to pull that off. And then those electrons are going here onto carbon. Follow? Anybody, any questions online? All right, let me ask you this. Let's say the pKa of that proton that's getting pulled off is 12. Right? Not a great acid, but a decent acid. Why? What is it about the conjugate base? After pulling that proton off, what can I do? How can I stabilize the conjugate base? That's the question I'm getting at.
Oh, you could break the double bond on attached to oxygen.
Okay, by resonance, you're saying?
Yes.
Yeah, you're right. So I can stabilize it like here, and here. Is that right? Or I can do resonance on this side as well. That's why that proton comes off. Right? So let's just calculate delta H for this reaction. What did I break? I broke a CH sigma bond, and I made an OH sigma bond. Is that right? You see the, does everybody see the OH bond here? That was made. The OCH3 picked up a proton and it became CH3OH. Right? And then I broke a CH sigma bond. What we got, Mike? You our statistician, our bond strength guy. Still learning. Oh, that's okay. So find the hydrogen. Is it in that at the top?
Oh, I see, okay.
And go across the oxygen and tell me what that number is. So we broke what we made. We made OH bond, that's 414, right? We broke it. That's for carbon, the CH bond. Okay, so we broke the CH bond. And we made a OH bond. What is that? 464? What we got? Negative 50? Is that right? Kilojoules per mole, that's delta H. Is that reaction gonna be spontaneous? Like, as far as activation energy is concerned, is it fast, is it slow? Exothermic, is it exothermic?
Is low,
Right,
and then the lower, the more spontaneous.
right. Is it exothermic?
It's exothermic.
Exothermic. So that tells you everything you need to know. It's gonna be fast, it's gonna have a KEQ greater than 1, and it's gonna have a negative delta G naught as well. All right, good. Now we're gonna do the second part, and we're gonna get the total delta H, right? So we're gonna sum up the two values and see if it comes out negative or positive. So if it's, to see if it's overall exothermic or endothermic. Because this is really all one big elimination process. All right. What happened in going from on the bottom reaction? What happened there?
They removed the bond between carbon and CO,
Okay.
and then they took that extra electron and formed a double bond
Okay.
with carbon.
Okay. So we got chlorine here. And we said up front, this was an elimination. So what is chlorine in this case? If I get rid of it, what is it? It's leaving group, right? So chlorine is the leaving group. You see over here, it left, and it's all by itself. In actuality, in terms of substitution and elimination, chlorine is excellent as a leaving group, right? And the way you tell that is to go back and look at what the conjugate acid pKa is for HCl. That'll tell you how good of a leaving group it is. Conjugate acid for HCl has a pKa of about -7, I think, -2, something like that. So it's an excellent leaving group. I don't know off the top of my head, but it's right there at the top of the leaving group list. Iodine is -10, and I think chlorine is somewhere around -2, -3. So super low pKa.
I was gonna ask, can you go back up to, what was your year? So I can see that, proton transfer.
Oh, yeah.
So,
All right.
so you drew an electron, an arrow from the oxygen, that right there to that.
To the proton. Mhm.
Okay.
And then the CH bond broke, and those electrons end up on carbon.
I got you.
All right. So over here, Chase said do this. Is that right? All right. So that's how I get you here. So let's calculate delta H for this reaction. Bonds broken minus bonds formed. What did I break?
Carbon, chloride.
Carbon chlorine bond, good. And then what did I make?
Carbon.
Yeah, a pi bond, not a sigma bond. There's a difference. If you look at the chart, pi bonds actually work more energy. So carbon-carbon pi bond being made is actually really good. Don't give off a lot of energy. So bonds broken, carbon chlorine. Bonds formed, carbon-carbon pi. What we got, Mike? The more you look at the chart, the more you're gonna be able to read. You're gonna be an expert. So 339 minus 837. It's 611. That's still a lot. What is that? 427 or 327? 227, is that right? I'm not 227, 272. I'm mixing the numbers up. Is that right? 272? There you go. Thank you.
Yeah, -272.
That was quick thinking. 272. And it's negative, right?
Yes.
Okay. So now when we look at this overall reaction, if we want to know the delta H, we're just going to sum them up. We're going to say minus 50 plus minus 272 for that 322. Is that right? Negative 322 kilojoules per mole. Is that right?
Yes.
That's a lot. That reaction is overall highly exothermic because remember I said earlier, the goal is to break weak bonds and make stronger bonds. And that carbon-carbon pi bond is a very, it's lucrative to make that. You get a lot of energy put back into the system or given off from the system by making that.
Dr. Russell. Hello.
All right, any questions from anybody? I feel like I'm at church.
Hello.
People on Zoom, YouTube, and in the building. Go ahead.
Hello.
Yes, go ahead.
Yes, I just wanted you to repeat what you had for that equation.
At the bottom, the overall.
Yes.
Okay.
Also, you just subtracted the first one. No, you added the first one and the second one.
1 plus delta H2. All right, this, let's say up here when we did this one, we'll call this one delta H1. That's the first delta H we calculated. And then down here, we calculated delta H. Here, this was right here. So we just took the sum of the two delta H values for each reaction to get the overall delta H.
Okay.
Yeah. So that's for that overall reaction, is it exothermic or endothermic? If the overall delta H is negative 322, it's highly exothermic. That means it's going to have a KEQ that's greater than 1, delta G that's also negative, and a very low activation energy. All right, questions about that? Any questions about anything we talked about so far? No, everybody good. All hearts and minds clear. Right? Let's go to, now, we're gonna have to do some recall here, but let's go to the next section of the handout, which is dealing with radicals. Then we're gonna start on a radical substitution reaction. But before we start that, we're gonna do a warm-up by understanding how bonds break in a radical fashion. If I break, let's take the top example. If I break that bromine-bromine bond and each bromine leaves with one electron, what do we call that process? It's homolytic. Good. All your radical processes are either going to be homolytic or homogenic. This is homolytic. Right, and I'm going to break it. If I have one electron here and one here, how do I break that bond? Remember, if one atom takes all the electrons, that's heterolytic. But in this case, it looks like each atom got one electron. So how would I depict that using curved arrows?
So one arrow.
The fish hooks. Yeah. Both, you can both correct. We use the fish hooks, so I'm going to show, Ross, tighten up. One arrow going here and one going here. Anybody not see that? That's online. Don't hesitate to unmute and ask. All right? So that's how I broke that bond. That's very important because when we get to the actual radical substitution reaction, the first step in that reaction is going to be a step just like this, where we take a halogen or take some other radical initiator and we break it in half like that. All right, let's go to the next example. What did I do here? Put them back together. How do I show that? Fish hooks from each radical coming together, right? And again, it might seem like rudimentary, but it's very purposeful because when we get to the radical substitution mechanism, all these little nuances come into play. So if I want to show a bond being made between two radicals, I put a fish hook here and a fish hook here. They kind of meet in the middle. Right, and that's how I show that bond being made, homogenic. Right, and that's why when we first started this section, that's why I started it off talking about both processes, polar and radical. We did polar first, and then we did radical after that, so we can get the terminology out of the way. All right, what happened here? Broke the pi bond and also did what? Formed the carbon bromine bond. Right? So let's see how we did that. And everything is radical. So everything is either homogenic or homolytic. So I made a bond, looks like between this carbon right here and bromine. Is that right? And then I put one electron on this carbon right here. I'm gonna change the color. I'm gonna clean all that highlight, all those highlights up off. Right? So we can show this in steps, or do you want me to show it directly? What would you prefer? All right. I was thinking that. All right, so let's do this. Let's show the double bond breaking. Like so. We're gonna have this. With a radical here and a radical here. Anybody disagree with that? All right, and I'm going to take that radical and I'm just going to react it with bromine like that. Notice I'm just drawing those two arrows coming together. What that means is that those two electrons are going to be shared between those two atoms. All right, questions, anything? And that's how I'm able to get you here. All right. Any bond, we can homolytically cleave it. And when we do, it's going to break up into its components, which are 2 electrons. Every bond is made up of 2 electrons. All right, let's see what we got down here. What happened?
Shared that floating that single electron.
Yep. So I made a sigma bond over here, didn't I?
Yeah.
And the way I did that is to take an electron from each one of those carbons and share it. Well, I'm doing this, right? Here, here. Those 2 arrows come together means I'm sharing a bond, sharing a pair of electrons between those 2 atoms, and I'm making a bond. All right, so I made a sigma bond on this side. All right, questions? Online, in person, doesn't matter. Anybody? Let me jog your memory too on something, because remember, anytime we make a bond, what's happening when I'm making bonds? Like what's the sharing electrons and overlapping orbitals every time. So this right here, this radical is really sitting in a p orbital on that carbon like that. Same thing here. So in order to make that bond, they have to overlap, right? So I know I have to draw them flat, but in reality, one of them is coming from one side, one's coming from the other side, where those 2 p orbitals can overlap and share that electron. All right. All right. Let's go to here. So these are important reactions right here. Very important reactions. And I'm going to explain why once we go through them. So what happened?
You substituted, you switched them out. So you took the single electron
Mhm.
from bromine and you put it into you replaced it with the hydrogen. Yeah, the hydrogen that's on top of the carbon.
Okay. So you're saying I took this hydrogen, I gave it to bromine to get this? Is that what you're saying?
Yeah, you love switch.
Okay. That's a good way to put it. I like it. And you're right. But it's not a substitution. It's similar. It's a precursor to substitution.
Okay.
Right? Because in order for it to be a substitution, I got to put something here in the place of that hydrogen. Is that right?
Yeah.
So it's a precursor though. So that's good. This process, you're going to see a million times when we're doing these radical substitution reactions. When I pull off a hydrogen with a radical, it's a process called abstraction. And the mechanism for abstraction never changes. It never changes. The way I want to show this, I'm going to do this. I'm going to draw 1 electron towards hydrogen. I'm going to draw 1 towards carbon. That's how I got that carbon radical. And then what's facilitating it is bromine. So I'm going to draw an arrow from there. So bromine is actually coaxing that hydrogen away from carbon.
It seems like there's like 10 more steps.
Oh, yes. Yep. Because you're moving the electron individually, so there are more steps. You're right. But it's the same outcome. Right? This is abstraction. This happens in every radical chain reaction. In the middle step, which is propagation. If you watch the video, you know what I'm talking about, propagation. So you got initiation step, you got a propagation step, and you got termination step. Is that right? So all propagation is abstraction. Any questions about that? How that happens? I homolytically cleave the CH bond, and then I homogenically make the HBr bond. That's how I got HBr on the other side. Anybody not see that? All right, let's look at the last example. That's the substitution part right there. Because now H is now Br in it. So how do I show that?
The half arrow from the lone electron. next to
Like that. They meet up, boom. That's a real rudimentary, elementary way of expressing it because it's really orbital on bromine overlapping with an orbital on carbon. Right, but you can see over here, I have a carbon bromine bond. So up here for the abstraction step, I want you to write this, that this is a precursor. Substitution. All radical substitutions happen through initiation, propagation, and then termination. So this will be an example right here in the bottom, termination step. All right, so the next time you hear something about antioxidants, scavenging free radicals, this is what's happening. So an antioxidant has a single electron, and it'll pick up a free radical by forming a bond with it homogenically. All right, let's go to, before we go, any questions? All right, we got 8 minutes. I'm only gonna take 5. Let this solve on me to pop up. Oh, never mind. But there is a radical document on Blackboard that's for radicals only. So reaction. But that's all right. We'll do it this way. All right, folks, let's talk about, I'm just going to introduce it. And then on Wednesday, we'll work through the handout. The handout also asks about calculating percentages of products and all that stuff, which I'll send that video to you. All right. So let's just talk about it now. Radical substitution. Right, and you saw this already if you watched that Pac-Man video. Right, it has 3 steps: initiation, propagation, and termination. Right, so overall, the reaction would be the overall reaction, and let's say I had pH 400 to get time from the video plus UR2. Right. Anytime I do a radical reaction, I have to do it in the presence of ultraviolet light. That's the only light that has enough energy to cleave a carbon-carbon bond, carbon-hydrogen bond, or an initiator bond. Most of the time, your initiator for radical substitution is going to be a halogen. So Br2, Cl2, I2, right? And so I'm gonna react this in the presence of light, H nu. Y'all remember that equation from GChem? Energy of a photon. The E equals Planck's constant times the speed of, not the speed of, the frequency of the radiation. So, which is C over lambda, right? Speed of light divided by the wavelength. You can substitute it in. But that's when you see that, that's a dead giveaway that the reaction is a radical reaction. It's a dead giveaway, right? Anytime you see H new present, that's telling you that your reaction is gonna be radical. Right, so then this is gonna end up giving me CH3 Br plus HBr. All right, somebody tell me what happens in the initiation step. Anybody? See, Cameron took notes. Come on, Cameron. Knock it out the park. What happens in the initiation step? So you're making a reactive radical. Which species is getting worked on in initiation? The halogen or the alkane? The alkane is here, the CH4. The Br2 is my halogen. So which one is getting worked on? In initiation, it's the halogen, right? That bond is easier to break than a carbon-hydrogen bond because halogens are big atomic radius, and the bond between them is really long and weak, easy to break. So initiation, I'm going to take bromine. And I'm going to break that bond homolytically. Right, so I'm going to do this. It's all a little familiar because it just did it. I'm going to get this plus this. Anybody not see that? It's a homolytic cleavage, and now I have a radical here and one here. And I want to clarify something too, right? Even though I'm only showing one bromine, right, and you only got two bromines here shown. In reality, if I started with 1 mole of bromine, that's Avogadro's number of molecules per mole, right? So I'll never run out. So think about that. And I'm saying that because sometimes you'll have a longer chain alkane that you're working on. And you're abstracting from multiple sites, but you'll never run out of bromine. All right. Now, propagation, what happens, Cameron? New radicals. For initiation, reactive radicals are made. Propagation. I just did the good news challenge, not on purpose. All right. Propagation, when this happens, I have a bromine that's going to come in and do abstraction. This is where abstraction happens. That's why I went over it in the initial example first, so we can, when you see it, you'll know it. All right. So what does that look like for this molecule? Abstraction. If I want to, let's say I'm taking off this hydrogen part. What does the abstraction step look like? It never changes, by the way. It's always the same 3 arrows. I'm going to break the CH bond homolytically. So each atom is going to get 1 electron. And then I'm going to make an HBr bond homogenic. So this is what's happening here. I'm going here and here. Is that right? Yeah. And then here. That never changes. So if you see this on the exam, when you get to the propagation step, it's the same 3 arrows no matter what hydrogen you remove. I'll put those two together, and then on the other side of the arrow, right, I have this CH3 CH3 dot plus HBr. So propagation, this is my new radical right here. That's my new radical. All right. Final step is termination. So I want to put together the new radical I made in propagation, this plus bromine radical. That's what happens, right? Homogenically, how do I show it? Here, right? That means I'm making a bond there, so then I get CH3. And overall, that's a radical substitution. I've substituted one of the hydrogens with what? Bromine. We zoom on it. One of the most common mistakes in doing this mechanism is putting HBr in the termination step. That doesn't happen. It's always a bromine radical. Right? You gotta stop. And this was productive. What do y'all think? I lost 3 people, but we got 21 left, so. Any questions?
So on the test, what we have to show each step?
Yes.
Okay.